When a transformer is located remotely from a panel and that panel is subsequently feeding a subpanel, specific grounding requirements must be followed to ensure electrical safety and compliance with the National Electrical Code, or NEC. Let's break down the grounding requirements for both the main panel, which is located near the transformer and serves as the service disconnect, and the subpanel, which is located in the building. Firstly, considering the main panel, also called the service panel, located near the transformer, you are required to install two grounding rods. These grounding rods serve as the primary grounding electrodes for the electrical system. According to the NEC, these grounding electrodes should be installed at least 8 feet apart. The purpose of having two grounding rods is to provide a redundant grounding path, ensuring that the system has a low impedance connection to the earth. Secondly, it is essential to install a main bonding jumper, or MBJ, at the main panel. The main bonding jumper is a conductor that connects the grounded conductor, which is the neutral bar, to the grounding terminal bar within the main panel. This connection is crucial because it establishes a common ground reference point for the entire electrical system. The size of the main bonding jumper is determined by NEC Table 250.102 cone and is based on the size of the service entrance conductors. Thirdly, a grounding electrode conductor, or GEC, must be installed to connect the grounded conductor, or neutral bar, to the grounding rods. The grounding electrode conductor provides a direct path for fault current to flow back to the source, facilitating the operation of overcurrent protective devices such as circuit breakers or fuses. The size of the grounding electrode conductor is determined by NEC Table 250.66, and it is based on the size of the service entrance conductors. Now let's discuss the grounding requirements for the subpanel, which is located in the building. Firstly, the subpanel does not require its own grounding rods. The subpanel is derived from the main panel and therefore relies on the grounding system established at the main panel. Installing additional grounding rods at the subpanel can create ground loops, which can lead to unwanted circulating currents and potentially introduce noise into sensitive electronic equipment. Secondly, the subpanel must be bonded to the grounding system of the main panel via grounding electrode conductor, or GEC. This grounding electrode conductor provides a connection between the grounding terminal bar in the subpanel and the grounding system at the main panel. It is essential to ensure that this grounding electrode conductor is properly sized according to NEC Table 250.66 and securely connected at both ends. Thirdly, an equipment grounding conductor, or EC, can be used to connect the metal enclosure of the subpanel to the grounding electrode conductor. The equipment grounding conductor provides a low impedance path for fault current to flow back to the source, ensuring that any fault in the subpanel and enclosure will quickly trip the overcurrent protective device. The equipment grounding conductor is typically a copper or aluminum wire and is sized according to NEC Table 250.122, based on the rating of the circuit supplying the subpanel. The concrete enclosed electrode, also known as a UFO ground, which you mentioned, can be used as an additional grounding electrode. A concrete encased electrode is a grounding electrode that is encased in concrete and is typically located near the foundation of a building. While the concrete encased electrode can provide additional grounding, it is not sufficient to eliminate the need for grounding rods at the main panel. The NEC requires that all grounding electrodes be supplemented by at least one additional grounding electrode, such as a ground rod or ground ring. The concrete encased electrode should be connected to the grounding electrode system using a grounding electrode conductor sized according to NEC Table 250.66. In summary, for this scenario, you must install two grounding rods at the main panel near the transformer, install a main bonding jumper at the main panel to connect the neutral bar to the ground bar, install a grounding electrode conductor to connect the neutral bar to the grounding rods, and install a grounding electrode conductor to connect the subpanel to the grounding system of the main panel. You may optionally use the concrete encased electrode as an additional grounding electrode, but it does not replace the requirement for grounding rods at the main panel. It's important to emphasize the function and sizing of the grounding electrode conductor. The grounding electrode conductor, or GEC, plays a vital role in providing a low impedance path for fault current to return to the source. This low impedance path is crucial for the rapid clearing of ground faults and the safe operation of overcurrent protective devices. The size of the grounding electrode conductor is determined by NEC Table 250.66, which takes into account the size of the service entrance conductors. It is essential to select the correct size grounding electrode conductor to ensure that it can effectively carry the anticipated fault current. The material of the grounding electrode conductor is also important. Copper is the most commonly used material for grounding electrode conductors due to its excellent conductivity and corrosion resistance. However, aluminum can also be used, provided that it is properly sized and protected from corrosion. When installing the grounding electrode conductor, it is important to ensure that it is securely connected to the grounding electrodes and the grounded conductor. Connection should be made using approved connectors and fittings that are suitable for the type of conductor being used. The grounding electrode conductor should be protected from physical damage and should be installed in a manner that minimizes the risk of corrosion. Another important aspect of grounding is the concept of impedance. Impedance is the total opposition to the flow of current in an alternating current circuit. It is composed of resistance, inductive reactance, and capacitive reactance. In a grounding system, it is desirable to have a low impedance path for fault current to flow back to the source. This low impedance path ensures that the fault current will be high enough to quickly trip the overcurrent protective device, minimizing the duration of the fault and reducing the risk of electrical shock or fire. The impedance of the grounding system is affected by several factors, including the size and material of the grounding conductors, the length of the grounding conductors, and the type and condition of the grounding electrodes. It is important to design and install the grounding system in a manner that minimizes impedance and ensures that the system is capable of effectively carrying fault current. Now, let's clarify the differences between the grounding electrode conductor, an equipment grounding conductor, and a bonding jumper. While all three conductors play a role in the grounding system, they serve different purposes and have different requirements. As mentioned earlier, the grounding electrode conductor, or GEC, connects the grounded conductor, or neutral, to the grounding electrode system, such as grounding rods or a concrete encased electrode. Its primary purpose is to provide a path for fault current to flow back to the source and to establish a common ground reference point for the electrical system. The equipment grounding conductor, or EG, connects the metal enclosures of electrical equipment to the grounding system. Its primary purpose is to provide a low impedance path for fault current to flow back to the source in the event of a fault in the equipment. The equipment grounding conductor helps to ensure that the metal enclosures of electrical equipment are ground potential, minimizing the risk of electrical shock. The bonding jumper is used to connect different parts of the grounding system together, such as metal water pipes, metal gas pipes, and metal building frames. Its primary purpose is to ensure that all metal parts of the electrical system are at the same ground potential, minimizing the risk of stray voltages and electrical shock. Bonding jumpers are typically sized according to NEC Table 250.102 current and are installed in a manner that provides a low impedance path for current to flow. Furthermore, the NEC provides specific requirements for the installation of grounding electrodes. Grounding electrodes must be installed in accordance with NEC Section 250.52, which specifies the types of grounding electrodes that are permitted and the methods for installing them. The most common types of grounding electrodes include grounding rods, metal water pipes, concrete encased electrodes, and ground rings. Grounding rods must be at least 8 feet long and must be driven into the ground until at least 8 feet of the rod is in contact with the soil. Metal water pipes can be used as grounding electrodes, provided that they are in direct contact with the earth for at least 10 feet. Concrete encased electrodes must be at least 20 feet long and must be encased in at least 2 inches of concrete. Ground rings must be at least 20 feet in length and must be buried at least 30 inches below the surface of the earth. When installing grounding electrodes, it is important to ensure that they are located in an area that is free from physical damage and that they are protected from corrosion. The grounding electrodes should be accessible for inspection and testing. In Massachusetts, the electrical code is based on the National Electrical Code, or NEC, with some state-specific amendments. It is important to consult the Massachusetts Electrical Code to ensure compliance with all applicable requirements. The Massachusetts Electrical Code is enforced by the Massachusetts Board of State Examiners of Electricians. It is recommended to consult with a licensed electrical contractor or a qualified electrical engineer to ensure that the grounding system is designed and installed in accordance with all applicable codes and standards. Improper grounding can lead to serious electrical hazards, including electrical shock, fire, and equipment damage. A properly designed and installed grounding system is essential for the safety and reliability of the electrical system. In addition to the requirements discussed above, there are also specific requirements for the labeling and identification of grounding conductors. Grounding conductors must be identified in accordance with NEC Section 250.119, which specifies the methods for identifying grounding conductors. Grounding conductors are typically identified by their green color or by green color with one or more yellow stripes. The labeling and identification of grounding conductors helps to ensure that they are properly connected and that they are not inadvertently used for other purposes. Periodic inspection and testing of the grounding system is essential to ensure that it is functioning properly. The grounding system should be inspected visually for any signs of damage or corrosion. The resistance of the grounding system should be tested using a ground resistance meter. The ground resistance should be low enough to ensure that the grounding system is capable of effectively carrying fault current. If the ground resistance is too high, the grounding electrodes may need to be replaced or supplemented. Understanding the purpose and function of each component of the grounding system is crucial for ensuring electrical safety and compliance with NEC. The grounding system is not simply a collection of wires and electrodes, it is a carefully designed system that plays a vital role in protecting people and property from electrical hazards. When working on electrical systems, it is always important to follow safe work practices and to use appropriate personal protective equipment, or PPE. Electrical work should only be performed by qualified and experienced individuals who are familiar with the NEC and other applicable codes and standards. Remember that electricity can be dangerous, and it is always better to be safe than sorry. Let's talk about the importance of maintaining proper documentation for the grounding system. Accurate and up-to-date documentation is essential for troubleshooting and maintenance purposes. The documentation should include a detailed diagram of the grounding system showing the location of all grounding electrodes, grounding conductors, and bonding jumpers. The documentation should also include the size and type of all grounding conductors and the results of any ground resistance tests. This documentation should be kept in a safe and accessible location and should be updated whenever any changes are made to the grounding system. Another important consideration is the impact of the grounding system on sensitive electronic equipment. Poor grounding can introduce noise into sensitive electronic equipment, which can cause malfunctions or data corruption. To minimize the risk of noise, it is important to use shielded cables and to install surge protective devices, or SPDs. Surge protective devices help to protect electronic equipment from voltage surges and transients, which can be caused by lightning strikes or other electrical disturbances. When installing surge protective devices, it is important to follow the manufacturer's instructions and to ensure that they are properly grounded. It is also important to be aware of the potential for corrosion in the grounding system. Corrosion can occur when dissimilar metals are in contact with each other in the presence of moisture. To prevent corrosion, it is important to use corrosion-resistant materials and to protect the grounding system from moisture. Grounding conductors should be made of copper or aluminum, and grounding electrodes should be made of galvanized steel or stainless steel. Connections between similar metals should be made using approved connectors and fittings that are designed to prevent corrosion. Regular inspection and maintenance of the grounding system can help to identify and prevent corrosion before it becomes a problem. In addition to the requirements discussed above, there are also specific requirements for the grounding of generators and other separately derived systems. A separately derived system is an electrical system that is not directly connected to the utility power grid. Generators, transformers, and solar photovoltaic systems are examples of separately derived systems. The grounding requirements for separately derived systems are specified in NEC section 250.30. In general, separately derived systems must be grounded in the same manner as service entrances, with the exception that the grounding electrode conductor can be sized smaller based on the size of the derived phase conductors. It is important to carefully review the NEC requirements for the grounding of separately derived systems to ensure compliance. We also need to touch on the subject of ungrounded electrical systems. While most electrical systems are grounded, there are some applications where ungrounded systems are permitted. Ungrounded systems are typically used in industrial settings where a high degree of reliability is required. In an ungrounded system, there is no intentional connection to ground. This means that a single ground fault will not cause a circuit breaker to trip. However, a second ground fault on a different phase will cause the circuit breaker to trip. So it is important to have a ground fault detection system in place to alert personnel to the presence of a ground fault. Ungrounded systems are more complex to design and maintain than grounded systems, and they should only be used in applications where the benefits outweigh the risks. Let's discuss the role of arc fault circuit interrupters, or RFCIs, and ground fault circuit interrupters, or GFCIs, in electrical safety. RFCIs and GFCIs are devices that are designed to protect people from electrical shock. RFCIs protect against arc faults, which are dangerous electrical conditions that can cause fires. GFCIs protect against ground faults, which can cause electrical shock. RFCIs and GFCIs are required in many areas of the home, such as bedrooms, bathrooms, and kitchens. When installing RFCIs and GFCIs, it is important to follow the manufacturer's instructions and to ensure that they are properly grounded. We'll address the importance of surge protection. Electrical surges can damage or destroy sensitive electronic equipment. Surges can be caused by lightning strikes, power outages, or other electrical disturbances. To protect electronic equipment from surges, it is important to install surge protective devices, or SPDs, at the service entrance and at individual branch circuits. SPD work by diverting surge current to ground, preventing it from reaching the electronic equipment. When selecting SPD, it is important to choose devices that are rated for the expected surge current and that are compatible with the electrical system. Finally, consider the importance of ongoing education and training. The electrical code is constantly evolving, and it is important to stay up to date on the latest requirements. Ongoing education and training can help electrical professionals to stay current with the code and to improve their skills and knowledge. There are many resources available for electrical education and training, including online courses, workshops, and seminars. By investing in ongoing education and training, electrical professionals can ensure that they are providing safe and reliable electrical services.